Hey everyone, and welcome. If you're getting ready for the AS Physics Practical Paper 3, you are in exactly the right place. Today, we're going to break down this exam piece by piece and turn what seems complicated into a really clear strategy for success. Let's get started.
So here's the game plan. We're going to hit 5 key areas. We'll start with a bit of an inside scoop, a prediction for your upcoming paper. Then we'll dive into the nitty-gritty, how to collect flawless data, the secrets to plotting perfect graphs, how to tackle error and uncertainty, and finally, we'll conquer that monster 6-mark evaluation question. By the end of this, you'll have a complete roadmap to nail this exam.
All right, let's kick things off with a huge strategic tip. Looking at the recent trends, what's come up before, and the theory papers for this series, all signs are pointing to the February/March 2026 paper being all about mechanics and materials. So what does that actually mean for you? Well, it means you can probably put those electricity experiments on the back burner for a little while. Instead, you need to go all in on skills like using the micrometer screw gauge and really get to grips with concepts like static equilibrium. That's where the marks are going to be. Okay, let's get into the skills, starting with question 1 and collecting your data. This is where you build your foundation. It's the simple mistakes right here that cost people marks, so we're going to make sure that's not going to be you.
Take a look at this. This is a real comment from an examiner's report. A student just misread the micrometer, and boom, the mark is gone. Instantly. A tiny little error like this at the very start can have a massive knock-on effect for the rest of the question. It just shows how critical it is to be precise right from the get-go.
So, how do you avoid that trap? Simple. Here's a 3-step masterclass. 1. Always check for a 0 error before you even start. 2. Remember that wires aren't perfectly round, so take at least 3 readings in different places and at different angles, then find the average. And 3, this one is so important, record your data with the right precision. For a micrometer, that's 2 decimal places in millimeters. So if a reading is exactly 0.4, you must write 0.40. Next up, the results table. It's got to be pristine. First, your headings. They must be quantity, then a solidus, then the unit. No excuses. Second, consistency. All the raw readings you take for one measurement have to have the same number of decimal places. And finally, if you're calculated values, a good rule of thumb is to use the same number of significant figures as your least precise raw data, or maybe one more.
Okay, so you've got your perfect data. Now what? Let's turn it into a perfect graph. The graph is so much more than just plotting points. It's where you show the examiner you can really analyze what you've found.
There are 3 golden rules here. First, pick a scale that makes your plotted points take up at least half of the graph paper. We don't want any tiny little graphs hiding in the corner. Second, use sharp, small crosses for your points, not big fat blobs. And third, when you draw your triangle to find the gradient, make it big. The hypotenuse needs to be more than half the length of your whole line.
All right, but let me throw a common curveball at you, one that catches so many people out. What on earth do you do if your scale means the x-axis doesn't start at 0?
This is what we call a false origin. And the single most important thing to remember is this. If your x-axis doesn't start at 0, you cannot, I repeat, cannot, just read the y-intercept from where your line hits the y-axis. It is a guaranteeing way to lose a mark.
So what's the right way? You have to calculate it. Simple as that. Once you have your gradient, your m, you just pick a point from your line of best fit. Substitute those coordinates into y equals mx plus c and solve for c. It is the only way to get that mark.
Okay, you've nailed the graph. Now you're facing question 2. And this is where things get a bit trickier. It's less about following steps and more about the real thinking part of physics, where you have to judge the limitations of what you've actually measured.
This right here is the perfect example. The examiner is pointing out that the student just wrote down the ruler's precision as the uncertainty, but they didn't think about the reality of the experiment. There was a clip in the way. It was hard to get the ruler in the right spot. To get the top marks, you've got to think about the real-world context, not just what the instrument says.
So the takeaway is, be realistic. For a tricky measurement like that, saying your uncertainty is something like plus or minus 2 to 5 millimeters makes way more sense than just saying 1 millimeter. It shows you're thinking like a physicist, not a robot.
Now, often in question 2, they'll ask you to test if a relationship is true. Don't sweat it. There's a simple 4-step recipe. 1. Calculate your constant k using 2 different sets of your data. 2. Find the percentage difference between those 2 values. 3. Tell the examiner what your condition for success is before you conclude. Something like, if the difference is less than 10%, the relationship holds. And 4, write a final sentence that clearly states whether your result met that condition or not.
And that brings us to the final boss of paper 3, the 6-mark evaluation. This is where they ask you to find the flaws in the experiment and suggest smart, practical ways to make it better. This is where an A becomes an A star. Okay, this slide is pure gold. Do not, under any circumstances, write vague things like human error or do more repeats. They are instant mark killers. You get 0. Instead, you need to be specific. Was the motion too fast to time accurately? The improvement is using a video camera with slow motion. Was it hard to read the ruler without parallax error? Suggest using a fiducial marker to line up your eye. Was the whole setup a bit wobbly? The solution is to clamp it to the bench with G-clamps. Specific problems, specific solutions. That's the key.
So when you boil it all down, everything we've talked about comes back to these 3 words. Precision, right down to the decimal places. Consistency in how you record everything. And specificity, especially when you're talking about errors and how to fix them. If you can nail these 3 things, you are well on your way to getting full marks.
And I'll leave you with this final thought. This exam, it's not just a test to see if you can follow a recipe. It's a test of your mindset. So as you practice, keep asking yourself this question. Are you just collecting data, or are you starting to think like a real physicist? You've got this. Good luck.